20 of CSE 548, the analysis of algorithms. Let's start off, first of all, with any sort of logistical questions. There's a midterm tomorrow, next class. Okay? That midterm will cover everything since the previous midterm. Okay? Which means basically backtracking, dynamic programming, and graph algorithms. Those are the big three things. It's possible some questions may involve knowing things from the first midterm, okay? But again, the things that we're going to be, so don't. It's not fair for you to complain if, oh wait, you asked us to sort something. What do I know about sorting? You're supposed to know something about what we did before the first midterm. But the questions that are really going to be interesting are going to be the ones since the first midterm. Okay, so if you want to study, you should be studying backtracking, dynamic programming, and graph algorithms. Okay, it'll be, again, same kind of test in the sense that it will be an open book, open notes test. Okay, it will be a similar number of problems. I have posted an old midterm from the last time I taught the course. So if you want to get some hints, that was an example of a previous midterm. There was one typo on that previous midterm on the problem about minimum spanning trees, where at one point when I talk about disconnected, I mean connected. Okay. Question number 3. So if you look at the problem, it didn't make any sense. The problem got dissed in one way or another. Okay. The problem was that at one point I asked sort of, you're deleting edges from the graph until, okay. Here's the problem. Okay. The problem was 3 about an algorithm for finding minimum spanning trees. And it was a question of an algorithm that basically starts out from the highest edge, deletes it until the graph, deletes it if the graph remains connected after deleting it. Okay? And so the point is that this should be erased. Okay? So it makes sense. If you read the question and understand why it gives you something correct, that'll do it. Question? I don't have solutions posted. There should be some, though, in the notes that are, I believe that people who posted have the notes from the previous semester. Okay, I guess there are printed copies of an answer key in that. Okay, so has anybody actually seen an answer key for this? Okay, so presumably there are answer keys in the notes that I originally gave out at the copy shop from the previous semester. And I'll try to get a copy of that and put that in the notes in the library. Okay, but we'll see about that. I'll see if I can do that. Okay. Any other questions? Yes, questions. Yes. Right now, since the homework is sort of done, what if you have one partner who does and one partner who doesn't? I guess you can do one of the, basically do what makes sense to you, and we'll figure out what makes sense to us. Somehow that's a funny situation. I'd rather so write down what happens, and we'll use our judgment at that point. I mean, in an ideal world, the person who's already used their partner, their extension shouldn't get credit for another one. On the other hand, in an ideal world, the person shouldn't get penalized for having a partner who was negligent on the previous one. So do what seems reasonable and turn it in, and we'll take off what seems reasonable to us. Okay? Any other questions? Question?
Is all pair shortest paths fair game?
All pair shortest paths will be fair game since I will cover it today. Anything I cover up to today will be fair game. Okay? And if you manage to stop me from covering it, then it's not fair game. Okay? So that may provide some incentive to ask questions. Okay. Any other questions about the exam or anything like that? It'll be in here. Now, one thing to note is that, again, it'll be in here. On the previous test, okay, there was one student who copied from another student, okay, and I decided not to actually tell that student that they'd been caught cheating, because I figured that it would be better to accumulate more evidence during the rest of the semester and surprise them after the final, okay? So if you are that student, okay, please copy again from your neighbor, so we have more evidence, okay? Okay. If you're not that student, do not, because again, that's why I had people hand them in order where we can look at their neighbor, okay, so we could look at everybody's paper and compare them, okay? So please be careful. The statements I said at the beginning of the semester about people failing for academic honesty violations is certainly still in hold. Okay, so be serious about that. We are watching. Okay, we didn't want to alert people. Okay, because we want to try to catch them again next time. But we Xeroxed their tests, and everything will be fine at the end of the semester. Okay, any other questions about the exams? Okay, very good. Well, I'd like to talk about today a shortest path problems. How do you find shortest paths in graphs? And shortest path problems come up in a lot of applications. They come up in transportation applications. You want to find the shortest path from here to there. In communications applications. But more than that, shortest path problems come up in applications where the graph structure is maybe not necessarily apparent. Okay? And learning to think of the world in terms of shortest path algorithms is a useful thing to do. So as one example, I'm going to show you an example of a problem I worked on where basically we used the shortest path problem to solve a problem in languages, okay, in actually user interfaces. What was the problem? We were interested in letting people type text on a telephone at one keystroke per letter. You know, on a telephone, you've got each key on the telephone has 3 letters, okay? And you could type out messages, okay, by simply typing it out on a keypad. But somewhere, somebody's got to figure out which of the 3 letters. If you just type the key 2, it could be A, B, or C. So if you wanted to unambiguously type text, you would have to hit more than one key, which is very clumsy. Or you could try to let somebody type one key per stroke, and then have a program try to figure out which key they meant to type. And this is a project we were working on, okay, where what we wanted to do was something like this. The input would be a sequence of phone tokens, that the numbers people type. For each thing, they would be separated by star characters. So the words were going to be separated by stars. We were going to take the input, break it up into regions that were separated by stars, so we had a list of each possible word. For each word, each token, series of tokens in a word, we would come up with all possible dictionary words that represented that. So for example, for the string 4483, there were 2 words in the dictionary that would be typed in that way. That's give and hive, for example. Okay? And for the second word in the dictionary, okay, which was 63, okay, that could be either of or me. Okay? And for the, for the last word, which was 7464, there were 3 words in the dictionary: ping, ring, and sing, all of which are equivalent when you type them in on a telephone keyboard. Yeah? Can I make the lamps a little brighter? Probably not. Let's see. I can focus it, make it more out of focus. But, and I can make it bigger or smaller. What? Rotate the fluorescent lamp. Is this doing anything that makes anybody happy? Yeah. It does? Okay, good. Okay, good. Okay. Okay. So for every sequence of characters, we came up with a word, a list of all the possible words. Okay. The thing is, in order to disambiguate it, we wanted to figure out which sentence makes more sense. Okay? So in fact, of all these possibilities, the sentence they meant to type in was give me a ring. Okay? They could have typed hive of a sing, but that doesn't make any sense. Okay? So we wanted to use grammar to try to disambiguate which sentence it is. Now, how do we do that? Well, we make it a shortest path problem. What shortest path problem? Well, first of all, you need a graph. Where is there a graph to find on these things? What are the vertices going to be? The vertices will be each possible word that we can have in each possible position. What are the possible edges that we can have? Okay. We'll have an edge between any word in the first spot and any word in the second spot. Since we know any sentence is going to include one of these, one of these, one of these, and one of those, we could model the problem by having a graph where there's going to be a set of vertices for each word position in the sentence, a vertex for each possible word in each possible position, and then an edge from a word in the ith position to the word in the I plus first position. And if we do it like this, every possible sentence is described by a path through this graph. Okay, does everybody agree with that? Now what we wanted to do was to figure out which is the best possible path, which is the thing that makes the most possible sentence, the most possible sense for a sentence. What we had to do now is assign weights to these edges. What would kind of make sense to assign for weights? Well, we know certain words like to be next to other words. Okay? For example, certain words, like if we take a look at these things, take a look at the possibilities here. Again, maybe it's a little hard to see. But it should be clear that give me would have occurred in English more often than give of. Okay? And hive of would have occurred less often than both, and hive me would have occurred less than both. By analyzing a lot of text, we could figure out how likely is it that we'd want to go in a sentence from give to me. Okay? And make that be the cost of an edge. The more popular edge that we'd want to go through would be a cheaper edge. We could have these costs reflect in our actual application. We did things in a fairly sophisticated way. We ended up factoring in grammatical constraints, knowing how often nouns like to be next to verbs or something like that. Okay? But the bottom line was that we came up with costs for each edge to make it how likely would we want to make that transition. And once you've got that, then the best way to interpret the sentence is going to be the cheapest possible walk, okay, which would be described as the shortest path from the left to the right. Okay? And there's a lot of different problems that can be modeled in this way. When you do speech recognition, they have an algorithm that works like this. Okay, when you do spelling correction, in a good way, language and natural language interpretation, language problems like this occur. Okay, and so you should be aware to look out for shortest paths make sense in lots of contexts other than distances and other things. Any questions about the application or why it works? Okay, fair enough. Now, how do we find shortest paths in graphs? Okay, well, first question that's going to matter is the graph directed or undirected? Okay, I mean weighted or unweighted? Okay, if we have an unweighted graph, okay, the cost of a path between two nodes, okay, is going to be equal to the number of edges in that path. Okay, so in an unweighted graph, you end up with a world where the distance between one node and another is sort of basically the path with the shortest number of edges. If you think back to what breadth first search did, breadth first search started out by starting from some root, finding all the vertices that were within one edge of it, then by exploring from here, found out all vertices that were within a distance of 2 of the root, before looking at any vertex that was a distance 3 from the root. So breadth first search explores the vertices, okay, in terms of their distance, the shortest distance from the root. Okay? And so if you have an unweighted graph, okay, you can find the shortest path from the root to anything else in linear time using breadth first search. That should be apparent, okay? Although if there's any questions, I'll be happy to answer that. The interesting thing to see is that shortest path problems get different and more difficult, okay, when we talk about unweighted graphs, about weighted graphs, okay? Because in a weighted graph, the weight of a path, okay, between two nodes is the sum of the weights of the edges. If we think about each edge as representing, let's say, the length of a road between two cities, okay, the shortest path between 2 points may not be the fewest number of roads you go on, but it basically says that the sum of the roads that you go on is minimized. Okay? So the important thing to see here is that breadth first search will not work when you have weighted graphs. Okay? Or breadth first search will do something, but there's no guarantee that breadth first search will find the shortest paths. Because if you can imagine a situation where you could have a link, one direct road, let's say you've got 2 roads here, one scenic route between 2 cities, that's a distance of 10, there may have been a way to do it by making a lot of edges, each of which are length 1. If you have 6 edges of weight 1 versus 1 edge of weight 10, the cheaper way to get here is by using a lot of edges rather than few. Okay? So it should be clear that the breadth first search thing does not work on directed graphs, on weighted graphs. Okay? Any question? How many people believe that? How many people do not believe that? Okay? This is a core thing to understand for why we're going to go through the rigmarole we're going to go through. Okay? Because we have to take care of the fact that shorter distances may involve more edges. Okay? Another thing to note here is that if we look for the shortest path between two nodes, okay, there can be a lot of different shortest paths between two nodes. Okay, there can be an exponential number of shortest paths between two nodes. Consider a graph that looks something like this. Okay, where everything was of weight 1. To go between here and here, we could either go up or down or up or down. At each point, we could make a decision up or down, okay? And the distance from here to here would be the same. So there can be an exponential number of different paths between here and there. So if you say, I want to return all shortest paths, it should be clear that you're stuck. That will not be something you can do efficiently. What we can do efficiently is report a shortest path between the root and every other node, okay? Knowing there might be other ones, but for most applications, so long as you have one, that's good enough. Okay? Any questions about that, or is that clear? One other complication in our sort of shortest path game is to think about what happens when you have negative cost edges. Okay? It may be that, let's say, you could imagine a situation where, in certain applications, it does pay to talk about, when you think about arbitrary graphs, there's no reason why, when we're talking about minimum spanning trees, for example, you couldn't have had an edge weight of a negative edge weight, okay? And the algorithm would have performed perfectly well, okay? Turns out negative edge weights have some problems when it comes to shortest paths, or makes things a little bit more complicated. Suppose there was a cycle in a graph where this edge was -3, this edge was 1, and this edge was 1. And we wanted to go between here and here. What is the cheapest path from S to T in this graph? Okay? Okay, it could be very large. Okay, yeah. Why might negative weight come in? Why might... Well, let's say that a negative weight was how much money you had to pay in tolls at each place. And at some place on one particular road, they actually paid you, okay, to ride it. Okay? This would be short. That'd be an example. Okay? They may think that's a silly example. The bottom line is that there are applications where these things arise. Okay? Because remember, when you're modeling problems as shortest paths, you shouldn't only think in terms of transportation problems. Think back to the case where we had, the sentence kind of a structure we had. Yeah.
I asked a question was better to have a negative edge or great value or plus edge small?
Well, if you have a negative cost, your goal is to try to minimize what the cost is. Okay? The bottom line here is that if you want to figure out what's the cheapest path from here to here, you could get a cost of 1 minus 3, 1, or minus 1 from here to here directly. But the bottom line is you could actually do better by looping around here and create a more negative path. Because you'll notice here in the graph we have a cycle, minus 3, 1, 1. If we start from here, if they're going to pay us money, if we have a choice of paying tolls or them paying us money, here they pay us $3, we pay 1, we pay 1. Okay, we're now $1 richer than we were before. If we want the cheapest way to go from here to here, what's the cheapest way to do it? Basically, keep driving around here an infinite number of times. So shortest paths with negative weights, you get into funny situations. In particular, you get into a funny situation or an ill-defined problem whenever you have a negative cost cycle in the graph. Okay? Actually, an application where negative cost cycles do come in, actually, although I don't want to maybe go into it too much detail, has to do with trying to find ways of, let's say, trading currencies. You know that in an arbitrage world, you can get a certain rate for going from dollars to pesos, and a certain rate from pesos to francs, and from francs to lira, and lira back to dollars. If you're a currency trader, you're looking for a path through this graph, okay, that's going to give you the best possible return, okay? Ideally, you want a situation where you find a path where you end up making more money by going through this thing than you would otherwise, okay? And in an ideal world, what you're really looking for is trying to find one of these negative cost cycles, because there you can just keep pumping money going back in there, okay? So that's an example where these issues of negative cost cycles in graph does arise in a reasonably natural way, okay? But the bottom line for here is you should agree that negative cost edges can cause trouble in shortest path problems where they did not cause trouble in minimum spanning tree problems, okay? Because minimum spanning tree, all we wanted to do was to sum up the weights of all the edges, okay? We wanted to minimize that, okay? And it didn't matter if we had a negative answer or not, okay? Any questions? In fact, you should be able to prove, one way to do it is if you took the most negative edge in the minimum spanning tree. Let's say that was minus 50. If you add 50 to every edge in the spanning tree, every edge in the graph, the minimum spanning tree of the new graph is going to be the exact same tree as it was before, only now you have the same edge weights. That's not true in the case of shortest paths, okay, for reasons like this cycles. Okay, any questions about that? So anyway, there are algorithms, okay, that one can find even in the textbook that handle the case where you've got negative weighted edges, okay? We are going to assume that all edges in our graphs are positive, just for simplicity. But realize you've got trouble if not, and you've got to go to a more advanced algorithm. Okay? Any questions about that? Okay. So how can we find the shortest path in a graph? Okay, between two nodes in a graph. And it turns out the same algorithm will basically work for directed and undirected graphs. Okay? The algorithm is called Dijkstra's algorithm. Okay? And it's going to give us a fast way to find the shortest path between any two vertices S and T. So you want to go from vertex S to vertex T. Dijkstra's algorithm is going to do it. And again, if you have an unweighted graph, do breadth first search. If you have a weighted graph, now we've got to get to this. The correctness of Dijkstra's algorithm is going to follow from two fairly obvious things. Okay? Although the correctness of it is hard to confirm for yourself unless you really identified these two factors. The first thing is, suppose we have the shortest path from S to T, and it goes through a vertex X. Okay? So we have the shortest path that goes from S, pop, 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 wanders through vertex X, pop, 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 wanders to T. In that shortest path from S to T, if that really is the shortest path from S to T, from S to X, the path we use from S to X had better be the shortest path from S to X. Okay? Why? Suppose there was a shorter path from vertex S to X than we used in this thing. Could that possibly have given us, could this possibly be the shortest path from S to T? No, because we would have used that, okay, shorter path there and reduced the total cost. Okay? So if you believe that, what this says is we have to build up the shortest paths to nearby vertices, okay, before we can build up the shortest path to a faraway vertex. Okay? Second property that we need to know is that if all the edges have positive weight, okay, avoiding these problems with negative cost edges, the distance from vertex S to X is going to have to be less than from X to T. Why is that? Well, every edge's weight is positive. These edges from here to here are going to be positive. Okay? Thus, we know the distance from here to here has to be less than the distance from there to there. Okay? Any questions? Both of these should be clear. Okay, but you should make sure you believe them. Okay? That said, Dijkstra's algorithm is really going to be based on a dynamic programming strategy. Okay? Okay, dynamic programming-like strategy. Where what we're going to do is we're going to store the distance from S to all nearby nodes. Okay? And once we know the cost of going from S, our starting point, to the nearby nodes, we use that information to find the shortest path to more distant nodes. Okay? So it's sort of a breadth-first search-like strategy, taking the weights into considerations. Okay? And we're going to be processing the nodes based on how far they are from the root. Okay? So in particular, let's think about it. What's the shortest path from vertex S to vertex S? Okay? What do you have to do to get from S to S as cheaply as possible? Okay? Stay there. If you had negative cost edges, that might not necessarily be true. Okay? Because it might pay to sort of loop through this place where they keep giving you more money. Okay? But if you've got no negative cost edges, okay, the shortest path is to stay there. So the distance from S to S is 0. If we now think about where all the edge weights are positive, the smallest edge incident to S, okay, which may go to some vertex X, is going to have to define the cheapest cost from S to X. Now, why is that? Okay, we've now got a vertex here that is S. Okay, maybe I'll zoom this thing in. We've got some vertex here that's a distance of 1. Here, a vertex's distance is 2. This is X. It's the cheapest adjacent to the cheapest X edge from the source. Is there any possible way to get to vertex X cheaper than by going directly from S? No. You could have an edge here. If this edge could be negative, it might be cheaper to go from here to here. But we know that any path that goes through everything else is going to be a cost at least 2. The cost of going to here directly is 1. We know that the cheapest edge, okay, from the start vertex to some other vertex, okay, that is going to define the shortest distance path in the graph from S to X. Okay? Any questions? Okay? Can I just make it bigger? Yeah, it's up here. Very good. Okay? So what's the idea that we're going to use? We're going to use an array. Okay? And this array is going to store the length of the shortest path that we have found to each node. Originally, for all vertices except S, the shortest path from S to everything that we know is infinite. Okay? The distance from S to itself is 0. What we're going to do, as soon as we establish the shortest path, in each iteration we're going to gobble up a new vertex and determine what the shortest path is to that vertex. Okay? Once we establish that shortest path to X, we can now go through, okay, we now know the shortest path from S to X, okay? We'll now go through all the edges from that to see if there is a better path from S to anything else going through our newly found vertex. Okay? Any questions? The algorithm looks like this. Okay? We start out, we've got a known set of vertices. Vertices we know the shortest path to. Okay? Consists only of our starting point. That's 0. You know, the distance there is 0. For every other vertex, we set the cost of getting there to be infinite. For each edge that goes directly from our source, okay, the distance to get from S to that vertex is at most the weight of the edge that goes from S to that vertex. It might be that there is a shorter way to get from S to some of those vertices by going around through someplace else. Right now we only know the shortest path to S, and we know that we can get to all the other vertices adjacent to S, okay, in a distance of at most S. Okay? Last is the vertex, going to represent the vertex that we have last added to our known set. What is the algorithm that we're going to be doing? until we have added our destination vertex to the set. What we're going to do is find which is the vertex that it is not known, we haven't yet added it to our known set of vertices, okay, yet which minimizes its distance from the source. What is our situation? Known corresponds to all the vertices that we know the shortest path from, S to them. Unknown are all the vertices that are not in known. In each case, there's going to be some vertex here, okay. These are all we know the shortest distance to, from S to them. There's going to be some vertices out here we don't yet know the shortest path to. But we know that if there is a shortest path, okay, it's going to be a path from this vertex to something else, and that the path from that vertex to the root is going to be the shortest path possible. Okay? So what we're going to do is find the vertex, okay, which is one edge removed from a vertex in known, such that that distance is minimized. Okay? So V is going to be the new vertex, okay, that we select. Okay? For each edge from that vertex, okay, we are going to see whether or not for any vertex that we don't know the shortest path to, okay, is it cheaper to get to that vertex X the way that we had done before or through our new vertex V. Those are the only two possibilities. The cheapest way to get to this vertex may have been through here. Now that we add another edge to our known set, maybe there's a better way to get through there. So what are we going to do? The cheapest way to get to X is either going to be not going through V, or the shortest path to V plus the cost of the edge from V to X. Okay? In each iteration, we're going to go pull out one new vertex and add that vertex to our known set, stopping only when, okay, we have found the shortest path to our destination vertex. Okay? Any questions about that? Okay? If we take a look at an example, okay, the example should be reasonable. Here we've got a weighted graph. Okay? We're going to try to find the shortest path from A to something else. Starting from A, what's the shortest? We know we can get to G at F at a cost of 9, G at a cost of 5, B at a cost of 2. What do we know about the shortest path to some other vertex? Okay? The cheapest edge from B, A to B, is 2. That's the cheapest edge coming from A. Is there any possible way we can get to B cheaper than by going directly through A? Okay? How many people see why there can't be a cheaper way? Okay? How many people do not see why there can't be a cheaper way to get to B? Okay? Might there be a cheaper way to get to F? Well, maybe. We don't know yet. Okay? But we know there can't be a cheaper way to get to that. Now, what do we know? Starting from A, it takes 2 units to get to B. Let's consider all the vertices that are adjacent to A and B at this point. We can get to F at a cost of 9. We can get to G at a cost of what? 5 or 8? Which is better? 5. How can we get to C? We can get to C at a cost of 6. So what we've got is a world where we have some vertices that are known, some vertices at which we have ways of getting to them, okay, by going through known vertices and one extra edge. The next vertex we pick is going to be what? Okay, I would say instead let's take a look. This is the underlying graph, but this is really what we now know. We know these vertices are known. We know the shortest paths to them. We know the shortest paths, the cheapest. We know that for every vertex here, we've kept track of what is the cheapest way to get within one edge from the fringe and one extra edge. Okay? So what's the cost of getting to vertex C? Well, not 4, 6. because we would have to go through first getting to vertex 2. So the cost of getting to C is going to be the cost of getting to B, which is 2 plus 4 or 6. The cost of getting to G is going to be 5. The cost of getting to F is going to be 9. Which is the next vertex that we know the shortest path to? Has to be G. There can't possibly be any doubt. We've proven that there can't be a better way to get to G by going through anything else. Because getting to anybody else and walking to G is going to cost greater than 5. Okay? So now what's our situation? Our situation now looks like this. What's the cost of getting to F? Still remains to be 9. What's the cost of getting to L? Okay? It could be 7. Okay? 5 plus that. What's the cost of getting to H? Okay? It is going to be 5 plus that. 10. What's the cost of getting to this? Which is the cheapest vertex we can next add to our collection? C. Is there any possibility that there's a cheaper way to get to C? Not from A. Okay? So each iteration we're going to be figuring out which is the next greatest vertex to add. The next cheapest vertex to add. Okay? And so what we have to keep track of, for every vertex that is not in the shortest path tree that we're building, okay, we have to keep track of what is the cost of actually getting there, okay, and doing that. And updating it, the only updates that we have to change, once we add this new vertex to our set, okay, which vertices can possibly have their shortest path distance affected? It's only the vertices that are adjacent to C. So now we have to say, look, H is the cheap. We can get to H now at a cost of 5 plus what it cost to get to here, which was 6. I now know how to get to here in 11. Is that interesting? Well, it isn't interesting because we already could have gotten there in 10. This vertex we could have gotten there before in an infinite number of steps. Now we can get to it in a cost of 8. Is that interesting? Okay. Yeah, I think so. Okay, so we write that down now. And for each vertex, what we're going to be maintaining is, for each vertex in the fringe, what's the cheapest way that we can get there? Okay, as represented by the distance to this vertex plus the cost of that edge. Okay, any questions? Okay, and again, if you want, I can continue this example. Okay, but I think it's pretty clear. Okay, each time we grab the vertex which is, we can prove, the next vertex we can prove we know its shortest path of. Okay, that's the idea for the correctness of this. Okay, any questions about that? Okay? Yes, question. So the question now, when you ask yourself now, how much time does it take to run this thing? A lot depends upon what kind of data structures you end up using. That should also be clear about data structures, the graph algorithms now. There is an underlying graph theoretic idea, okay, and then there is the speed which it runs depends upon what kind of data structures you use. Okay? Let's look at the program and see how much time it takes. Okay? What is it that we want to be able to do? Okay? And there's a couple different ways we can implement it. We've got a loop here. This is going to go around how many times? Okay? This central loop here where we add one vertex at a time. How many times might this loop go around? Okay? How many? Number of vertices. This loop could go around n times. Okay? Because it may very well be that the vertex you're looking for requires going through n intermediate edges. Okay? We have to now select for each vertex which is the vertex which is of minimum cost. Okay? So this, one suggestion was we could use a heap. Okay? Since we're going to want to figure out which vertex is it that's not in our collection that we know the cheapest way to go to it. One possibility would be to use a heap. But another possibility, which is maybe the simpler possibility, would be we just use an array. Okay, we use adjacency lists, and we use an array where for each vertex, we know what the cost of going to the cost of getting to vertex I is. Okay, so basically an n-element array where D sub I is the cheapest way to get there. It maintains the cheapest cost we know of. How much time would it take if we used that simple array implementation to select for each vertex which is the cheapest unknown one? How would we do it? Okay? Right, now for every vertex in the graph, we know vertex 1, 2, 3, 4. We know the cost of getting to here is 8, 10, 15, 3. You want to look through each one of these and find the minimum. Okay? This could be done in order n time. Correct? If you represent the distances such that for every vertex the distance is associated with it directly, this would take order n time. For each edge going out of that vertex, we have to update these costs. How much time will be spent doing that if we have an adjacency list? How many edges will we have to update going out of a vertex? Okay, it's the gray, which is at most order n. For each one of these, how much time is actually going to be spent updating this thing? I've got to compute the minimum of this plus this plus this. Adding two numbers together, the minimum of two numbers, constant time, n, potentially at most n operations. This takes n time. Okay? What's the time that this algorithm takes, Dijkstra's algorithm takes, if we use a simple data structure? Okay, n squared. Because for each one of these vertices we peel off, we're going to be doing a linear amount of bookkeeping to find the shortest possible path. About the way to get to a new vertex. Okay, linear sweep through it, and then updating all affected costs. Okay, it should be clear that using a Boolean array, basically, or not a Boolean, an array associated with an array element associated with each vertex. Okay, we can do this in n squared time. Okay, any questions about that? Okay, one reason why there may be no questions. Very familiar to you. This n squared algorithm looks an incredible amount like Prim's algorithm. Okay? What was Prim's algorithm for minimum spanning tree? Start from some vertex, find the edge which is cheapest, the vertex we can get to cheapest from our current tree. Okay? And in each iteration, pull off the cheapest remaining vertex. Basically, this is Prim's algorithm, with one very small modification. Okay? Can anybody see where the modification is? The thing that makes this different from Prim's algorithm. Okay, think about it for a second. Okay? Any ideas?
Well, this might stop a lot faster.
It might stop faster because you say I'm only looping around till that. But potentially I'm going to loop around forever, so that's not really the problem. Okay, that's not really the interesting difference. Yes. The difference is here. Here, what I'm saying is the cost of going to x is the minimizing the cost of currently going to x, or the cost of going to v plus the cost of adding that edge. What does this look like in the minimum spanning tree algorithm? Okay, I minimize the current way of going to that, or the cost of the newly discovered edge that I can consider. If there's a new edge to link in that vertex that's cheaper, it doesn't matter how long a path it took to find that edge when you're looking at minimum spanning trees. All you want to do is grab the cheapest way to bring that vertex into the fold. So the amazing thing is, this really is Dijkstra's algorithm. Okay, Dijkstra's algorithm really is Prim's algorithm. Okay, except for, okay, so once you learn one, you should be able to learn the other. Okay, but it's important to sit down and convince yourself why both of them are correct, even though they're really so similar. Okay, any questions about that? How many people see that? Okay, how many people do not see it? Okay, any questions? Okay, so the bottom line is in n squared we can use the simple okay, to compute shortest paths. In fact, by using more advanced data structures, we can actually implement this basic algorithm even faster. Okay? Why is that? Take a look at what the basic algorithm is doing again. Okay? At each point, we're trying to figure out which is the next best vertex to add. The next best vertex to add, okay, is going to be the one of lowest cost. As was suggested, you could stick each vertex in a heap, okay, and order the vertices according to what their cheapest cost of getting at them is. And then, whenever you modify the distances, you're going to have to change their position in a heap. So the bottom line is that there is a faster implementation. Okay, I don't really want to go into it in too much detail. Okay, but it should be able to convince you that it's going to run in something like, okay, order m log n. Why is that? The log n is going to be coming from the time it takes to maintain the heap. You've got a heap on the vertices as ordered by their distance from S. Okay? In each iteration, you're going to want to select the top of the heap. That's going to be constant time. You're then going to want to update the costs of each of these other vertices. Now, what does that mean? That means that for every edge that vertex, that might affect the cost of one of the vertices in the heap. Okay? Instead of taking 50 units to get here, now maybe it only takes 40 units because there's a cheaper way through this thing that I've discovered. So what would I have to do? The simple thing to do would be to delete this vertex from the heap, okay, and then re-add it with the new cost. Deleting it from the heap and inserting it from in the number of nodes. Okay? And since I might do that for every edge that I consider, you should sort of believe that m log n is possible using fancier data structures. Okay? And I encourage you to sit down and convince yourself of that. Okay? But this would only be faster if you've got a very sparse graph. Because again, you've got n squared versus m log m. If the graph has n, Dijkstra is better. If you've got a very sparse graph, the new version of Dijkstra's graph is better. Okay? Any questions about that? And finally, if you really get carried away, there's a super modern data structure called the Fibonacci heap that was built because they observed that whenever you were using it in Dijkstra's algorithm, the items in your heap are only going to decrease. They're never going to increase. And so the Fibonacci heap permits a very fast operation for doing decreasing. Okay. Very complicated data structure. I don't want to go into it. Okay? But if you do go into it, okay, in fact, you can actually do shortest path in time that's n log n plus order m. So linear in the number of edges plus basically sorting time in the number of vertices. Okay? Any questions about that? Okay? It's important to see the n squared version and ideally to at least get an inkling that you can use other data structures to implement it faster for sparse graphs. Okay? Any questions? Okay, very good. So that said, now we can look at what was supposed to be the problem of the day. What was the problem of the day? Given a graph like this, okay, find the book gave this graph and said showed two shortest path trees. The problem of the day is find two more shortest path trees, or four different shortest path trees in this graph. Now, what do we mean by shortest path tree? Notice something kind of interesting that falls out of Dijkstra's algorithm. In Dijkstra's algorithm, what do we know about every edge that we are adding to the graph? Okay, when we go through and we update costs, every edge we add is going to be going from a vertex which we know the shortest path of, to, namely a known vertex and an unknown vertex. Correct? Those were the edges that we ended up finding interesting in Dijkstra's algorithm. if we keep track of those edges have to form a tree. Why not why can't that edge, that graph have a cycle in it? Because if white vertex to a black vertex, okay, there's no way that you can go back from the black to the white. Okay, you're always going from known to unknown. Okay, and thus there can be no cycles. And if you run it to completion, you will eventually visit every vertex. So the important thing to see is that Dijkstra's algorithm is generating shortest path trees. Okay? And here it's basically asking us to find shortest path graphs. Well, what do we know? How can we find the shortest path trees? My claim is we can run through Dijkstra's algorithm and see exactly where Dijkstra's algorithm has two equivalent vertices to choose from. Okay, once we have two equivalent vertices to choose from, we could choose either of them. That will give us a way to make different trees. So how does this work? Here is our graph. We're going to start from vertex S. First edge that we're going to pick up in Dijkstra's algorithm. Going from S to U. That's forced. There's no choice about it. I can either pick 3 or 5. Which is cheaper? 3. Now what do I know? I can go to vertex X at a cost of 5. Or I can go to vertex X at a cost of 4. Okay? Did I get these arrows backwards? I mean, in copying it, did I get the arrows backwards? I'm suddenly afraid. Okay. In the textbook, does anybody have the textbook open to this picture? Let me take a look. Sorry. Okay. Sorry for a second. Right. Okay. It looks like I botched this up. Graph. If you take a look at this thing. Oh wait. Suddenly I'm confused. Sorry about that. Hold on. Right. See, the cost over in the original graph, it went from to one edge went from 2 to that, and 1 went back. So I got my arrows backwards. Okay. So what's the cost of this? What's the cost of getting to X? Okay. We could do it at a cost of 5 like this, or a cost. Doesn't make any difference. So we could build 2 different trees, one of which starts going like that, one of which starts going like this. Correct? Because we could either get to it by adding this edge and now saying we know how to get here in 5, or get to here in 5. Doesn't really matter. Okay? So that gives us 2 possible choices of a tree. Now that we tree, what's the next edge that we're going to want to add? Okay? How much time will it take to get us to here? We could get to here at a cost of 9 by going 5 plus 4. Or we could get to here at a cost of 9 in terms of 3 plus 6. Which is better? Same. So my claim is that we could add either this edge or that edge. And it doesn't really matter which one we add. Bottom line, we could add either of them. Okay? And so my claim is that that gives us 4 spanning trees right now. 4 shortest path trees, each of which are equivalent. By choosing which one of these we want, or which one of these, and which one of those we want. 4 different trees depending upon which we pick. Any questions about it? We now know we can get up to here at a cost of 9 to complete the job. Down to here we can do that in a cost of 11. Or we could go from here at a cost of 5 plus 6. In fact, there's 2 different choices to get to here in 11. So in fact, there are 8 different spanning shortest path trees, all of which are equivalent. Any questions about that? Okay. So again, Dijkstra's algorithm is not that hard once you understand it and understand the shortest path, its relationship to Prim's algorithm. Okay, and I urge you to figure that out. Yes?
I cannot remember this algorithm, but where you do a topological sort first.
Right.
on the graph, and then that result to find the shortest path a lot quicker.
Okay, in a directed graph, okay, there's some in a directed acyclic graph, okay, which is something that you could do a topological sort on. In fact, there are faster algorithms for finding shortest paths. Okay, I don't want to go into that. That actually it makes a good homework problem, okay, or a good exam problem, okay, because it's actually not that complicated. Okay, I won't give it to you on the exam. Don't worry about that. Okay. But it should be clear that if you've got no cycles in the graph, there's less ways you can run into trouble, okay? And so potentially it becomes simpler. And finding shortest paths on directed acyclic graphs turns out to be very important. Think back to my sentence application way at the beginning. My sentence graph have any cycles in it? No, because all edges went from left to right. So in fact, you knew that the edge, that this graph was a DAG, and that in fact we didn't really need to even use a full-blown Dijkstra's algorithm, because you could use a topological a algorithm suited for DAGs, okay, that would run in linear time in the number of edges and vertices. Okay. Any questions about that? Okay. Now, one thing to notice here is that what did Dijkstra's algorithm give you? Dijkstra's algorithm gave you, for any vertex, okay, it enabled you to find the shortest path from that vertex to every other vertex. That is what Dijkstra's algorithm did. Now, in many algorithms, applications, you want to find the shortest path between every pair of vertices. Like, for example, suppose we have a road network that looks like something like this. I don't know what it is. Let's say it's this. Road network, okay? You want to figure out where you should place a McDonald's, okay? Where do you want your McDonald's? You want your McDonald's such that everybody is going to want to go to McDonald's, okay? You want to make sure nobody has too far to drive. What is the best place to put your McDonald's? Okay, in the middle. So, okay, it seems to me that the middle of the graph, okay, is defined by the vertex which minimizes the maximum shortest path distance to every other vertex. Okay? Okay? The middle vertex would in some sense be the one that if you took a look at all the shortest path from this vertex to every other vertex, we the maximum of those lengths. Okay? So if you think about it, you have one vertex. Let's think about it. You've got one vertex, V1, that can get to the other two vertices. One took 5 units, and one took 10 units. V2 could get to the other two vertices, took 1 unit and 100 units. Okay? Which one is more in the center? Okay? My claim is that the one that you want to make sure that there's no other vertex that's too far from the center. That's really what the center means. Okay? So the right kind of definition of the center is you would like to take a look from the center at the shortest path distances to every other vertex. And you'd like to pick the start that minimizes the maximum one of those. Okay? Why is this not the center? The reason is that to get out to here, this guy has a lot longer to drive to get to here than anybody had to get to here. Okay? So again, there's lots of different ways you can define the center. Okay? I think you could, I gave one that I think is reasonable. But it should be clear that in order to make a judgment about what the center is, you need to know for every vertex what its distance is to every other vertex. Okay? That should be clear is a useful thing. Okay? In trying to decide where to put down McDonald's. Okay? So how can we use Dijkstra's algorithm to find that out? Okay? Well, what will Dijkstra's algorithm tell us? We have to specify a starting vertex. Once we've got a starting vertex, How much time will it take to find the distance to all other vertex from that starting vertex? Okay. How much time? N squared. Okay, because that's how much time Dijkstra's algorithm took to run. If we want, that would tell us from S to every other vertex. If we want to know from every vertex to every other vertex, we've got to run Dijkstra's algorithm n times, once with each vertex as the source. Okay? And so that would mean n times running an n squared algorithm should mean that we can find the all pairs shortest path solution in n cubed time. Okay? How many people believe that? How many people do not believe that? Okay, that should be obvious. Okay? It just means that Dijkstra's algorithm will give us from the source to everybody else. If you want to find from everybody to everybody else, you just got to try everybody else as the source. Okay? Now, you could do this, but it turns out that there's an amazingly slick, cute, interesting dynamic programming algorithm that solves the all pairs shortest path problem in n cubed time as well. Okay? And I want to go through that, okay, because it'll give, I think, some practice to people in dynamic programming, which I know people probably could use. Okay?
Why is the amazingly slick program as bad as the stupid program?
Well, the slick algorithm will in fact be faster in practice because it's so simple and slick that you don't have to use fast data structures. Okay? I mean, this is going to be a 3 or 4 line algorithm. It'll do everything. Okay? So it's a little faster in practice, but at the very least, even if you forget about practice, you should just look at it and admire, wow, this is slick. Okay? And you can understand its slickness once you understand dynamic programming. Yeah. It is not going to be based on Dijkstra's algorithm at all. No. Okay? This is not Dijkstra's algorithm. It doesn't give us, Dijkstra's algorithm will give us the shortest path from the start to everybody else quickly. Okay? But it doesn't help you in finding the shortest path from any other starting point to something else. This algorithm will enable you to find the shortest path from all A's and B's, but it won't help you find all the shortest paths from S to everything else faster than finding all the shortest paths in the graph from all pairs shortest paths. So if you want just from a root to everybody else, you're better off with Dijkstra. But if you want to figure out where to plant your McDonald's, okay, you're better off with this Floyd's algorithm. Okay? Any questions? But let's look how we develop it, okay, because it's a dynamic programming problem. Okay? And dynamic programming, okay, I know people have trouble with. So what's the idea in dynamic programming? Okay? The basic idea is that you want to figure out, I mean, to characterize the structure of an optimal solution, that's sort of a vague term. The real idea is you want to come up with a recurrence relation where you figure out, I want to find the solution to my problem based on being told something about the rest of the problem. So I want to somehow figure out what is my answer in terms of smaller answers. That is the idea of that is a recurrence relation. Basically what I want to do is recursively define my recurrence relation. Once I have it, then there's the issue of how do you evaluate it, how do you fill in the table, in what order, okay, and get what the information you want. Okay, so what is the all pairs shortest path problem? What do we want to be able to know? We want to be able to know for all pairs I and j, what is the cheapest cost from going from I to j. That's what we mean by the all pairs shortest path cost. Given an adjacency matrix of a graph, we can construct the following matrix. Okay? The cost of going from I to j is going to be 0 if I equals j. Okay? Which makes sense. The distance from I to I is 0. We can say that the distance from I to j is going to be the weight of that edge, okay, from I to j if it exists. And the distance from I to j is going to be infinite if there is no edge directly linking those two vertices. Okay? This is going to be an initial matrix that we build. What does this matrix tell us? My claim is this matrix tells us what the shortest path is from I to j without going through any intermediate vertices. Correct? What is the shortest path between I and j if we're not allowed to use any intermediate vertices? Well, basically, it's the cost of the edge from I to j. There's no other way to get there. Okay? So if there is not an infinite an edge between them, it gets infinite. Otherwise, we get that edge. That's what the starting matrix is. Correct? It tells us the shortest path going through no intermediate nodes. Okay? Now let's think, how can we characterize what we mean by the shortest path between two vertices? Okay? There's lots of different ways we can do it. Dijkstra did it in one way. Think about the following idea. If we have the shortest path from I to j using at most m different edges, okay, what do we know about that? Okay? We know that the shortest path from I to j using at most m edges is going to be the shortest path from I to k for some k using at most m minus 1 edges plus some edge from k to j. Why is that? We want the shortest path from I to j using at most m edges. If so, what do we know? There is going to be some edge involved with it. Okay, if we take this shortest path, we know that the shortest path from here to here, if we peel off that last edge, if this has at most m edges, the shortest path from I to j has it's going to be built from the shortest path from I to k that uses at most m minus 1 edges. Correct? Right. Okay. So my claim is the shortest path from I to j using at most m edges, okay, is going to be a shortest path from I to j, I to k using m minus 1 edges, okay, at most, and, okay, that last edge. So the cost of the shortest path from here to here using at most m edges is going to be what? The cost of the shortest path to some vertex using at most m minus 1 edges plus that last edge that you use. Okay? How many people see what I'm saying? How many people do not see what I'm saying? Okay? That said, I claim this will give us a recurrence relation. Okay? And I want people to understand the recurrence relation. Okay? Let dij superscript m represent the shortest path from I to j using at most m edges. How many edges is this going to be from I to j? At most m. At most m means it could be 1, it could be 2, it could be up to m. Can't be m plus 1. What is the shortest path, the length of the shortest path from I to j using 0 edges? Okay, what does this matrix look like? Okay, it's going to be 0 if the entries will be 0 if I equals j. Otherwise, it's going to be infinite. Because how can you get from I to j using 0 edges if they're different vertices? You can't do it. Okay? So, how many people believe that this is true given our definition? Think about this. This is important to think about. Okay? How many people see it? How many people do not see it? Okay, good. Now we want to come up with a recurrence relation. Okay? We want to be able to figure out what is the cost of going from I to j using at most m edges in terms of, suppose we know how to do it using at most m minus 1 edges. What do we know? The cheapest way to go from I to j using at most m edges is either the cheapest way to go from I to j using at most m minus 1 edges. It may be that you don't need to use m edges going from here to there. Okay? Suppose we have a graph here that looks like this. This is vertex 1, vertex 2. What is the shortest path from vertex 1 to vertex 2 using at most 5 edges? Okay? What is it? 1, this. Okay? What is the shortest path from here to here using at most 100 edges? From here to here. What's the shortest path using 1,000,000 edges? It doesn't necessarily change. But on the other hand, what's the shortest path? As you add more edges, it might change. So what's our occurrence relation going to look like? We want to know what's the shortest path from I to j using at most m edges. It is either the shortest path using at most m minus 1 edges, or it's actually going to use m edges. If it uses m edges, what do we know? It's going to go through some vertex k. The last edge is going to go from some vertex k to j. Okay, right? What's the cost of that path? The cheapest path from I to k, using at most m minus 1 vertices, plus the cost of that extra edge. Okay? So my claim is that the shortest path from I to j using at most m edges is going to be over all k, minimizing the cost of going using at most m minus 1 edges plus that last edge. Okay? So basically over all possible choices of the next to last vertex, which is it that gives me the best performance? Okay? And this recurrence I claim is correct. Okay? Question?
I'm sorry, I don't understand. Go from the first slide.
How did I go from the first to the... I did something a little tricky. Okay? How did I go from here to here? Well, I have the minimum of this and this. The important thing to see is what's the cost of going from vertex k to vertex k. Okay? So if I permit k the cost of going from a vertex to itself to be 0, the shortest path from vertex 1 to vertex 2 using m edges can be thought of as going from 1 to 2 to 2 to 2 to 2 to 2 to 2. Okay? So by permitting the cost that that actual edge is 0, I can collapse these two cases into this one case. Okay? That's how I went from here to there. Okay? But the important thing to see is that in any path using m vertices, there's going to have to be a next to last one. I minimize over all choices of the last one, and then use this. Okay? If so, I have a recurrence relation. How many people believe the recurrence relation is correct? How many people do not believe the recurrence relation is correct? Okay? If we've got a recurrence relation, can we evaluate this recurrence relation? My claim is yes. Okay, why is that? Notice, ijm, m minus 1. Okay? If we have this value for all m minus 1 terms, the following loop will do it. The cost of going from I to j using m edges is initially infinite. Then what are we going to do? For all values of I and j, we want to figure out what's the cost of going from I to j using m edges is going to be minimizing this recurrence. This loop's going to go around k times for each value of I and j. If we have the values, all values for m minus 1, we can compute all values for m. Which means if we have all values for m equals 0, we can compute all values for m equals 1. Once we have all values for m equals 1, we can compute all values for m equals 2. Dot, dot, dot. Okay? My claim is this recurrence is correct, and we can evaluate it. Okay? How many people believe? How many people do not believe? Okay? Any questions if you don't believe?
What does it say over there? D sub ij. You corrected yourself there.
That was supposed to be not 0. That's supposed to be an m.
That's supposed to be there.
M. Yeah, I mean, we're interested in the mth term.
Yeah.
Okay, that's a typo. Okay? So what's the point? This algorithm, if we run it, will take ijk. This will take n cubed time in going from m to m plus 1. Okay? Does everybody agree with that? We've got to fill in all possible values of I and j. Okay? And to do that, we're going to have to evaluate all possible choices of k for each one. If we do that,
When do you change M?
what?
When do you change your set?
I don't change m. That's a little catch. Okay? Since the shortest path is going to use up most m possible edges, I have to, in fact, run that algorithm n times. First for m equals 1, then for m equals 2, then for m equals 3, then for m equals 4. Okay? So in fact, what I've got is an n cubed algorithm that has to run n times in order to give me the shortest path from I to j for all pairs. Because the real shortest path may use anywhere from 1 to m edges. So in fact, if you use this recurrence relation, I've just given you an n to the 4th algorithm for all pairs shortest path. That's bad. You could do it simpler with Dijkstra's algorithm. Okay? But it's worth developing this, first of all, to get some intuition and realize just how slick Floyd's algorithm is going to be. Okay? And to make sure you understand dynamic programming. It's another example for you to practice on. What is the real slick solution? The real slick solution, notice, is this. Yet another way to characterize the shortest path from I to j, okay, is as follows. Let d sub ij superscript k be the shortest path of length achievable from I to j by only using vertices 1 through k as intermediate vertices. Before, we were counting on the number of links we used, going from I to j. Now we're going to come up with a different recurrence relation, where we want to know what is the shortest path from I to j using vertices 1 through k as intermediate vertices. Okay? So what's going to happen? We give all the vertices in our roadmap numbers. Okay? At first, we're interested in what's the shortest path from here to New York City going through Washington, D.C. Does Washington, D.C. help? No. What is the shortest path from here to New York City going through Washington, D.C. and Vancouver? Does it help? No. What's the shortest path from here to Washington to New York City going through Mineola? Well, now maybe that helps. Okay? So what is the point here? We're going to eventually consider all the vertices as possible intermediate points. Okay? But at each point, we're only going to consider one new vertex as an intermediate candidate at a time. So what's the shortest path from j to j using only vertex 0, which doesn't exist, as an intermediate vertex? There's no intermediate vertices. The shortest path from here to here can only be those consisting of a direct edge. So the shortest path is going to be simply the weight of that edge. In general, if I add a new vertex as a possible intermediary, there's two possibilities. If I now say you now have the freedom to drive through Vancouver, there's two possibilities. Either it will help you to drive through Vancouver, or it will not help you to drive through Vancouver. If you now have a choice of k possibilities to drive through as intermediate points, you could say, well, I preferred the path I got by driving through one of the, not driving through Vancouver. Namely, the shortest path from I to j using the first k vertices might be the shortest path from I to j using the first k minus 1 vertices. Okay? Or it might be using that kth vertex. In which case, what's the shortest path from I to j using at most k, the first vertices 1 through k as intermediate vertices? Well, if we know we're going to go through k, we want to know that that's going to be the shortest path from I to k plus the shortest path from k to j. If we're going to find the shortest path from I to j that goes through k, this has to be it. Okay? So there's two possibilities. Either we don't use the kth vertex as the intermediary, or we do use the kth vertex as the intermediary. Is there any other possible option? No. Okay? So we want the shortest path from I to j either using k or not using k. This gives us an alternate recurrence relation. Okay? That when you think about it, has to be correct. Okay? How many people see the recurrence relation? How many people do not see it? Okay, are there any questions about that recurrence relation? Okay? Thinking about it, remember, think about what it is. The difference here is we talk about what are the possible intermediaries. Once we have that recurrence relation, the amazing thing is this recurrence relation is fast to solve. Why is that? We're going to want a loop. K is going to go from 1 to n. This is how many intermediate vertices we're allowed to use. For each I and j, what's the cost of evaluating this? We want to know the shortest path from I to j using k as an intermediary. Either we don't use it, which means we look it up from a table, or we do use it. But if we do use it, there's no decision to be made. The shortest path using k means we've got to get to k and we've got to get out of k. So in constant time, we can decide which of these two is the better option. Not linear time like it was before. And the bottom line is we have 3 loops. Okay, this is the entire program. And in n cubed time, you can compute the shortest paths. Okay, any questions about that? Question?
You're only adding this new edge as the last possible.
Right. No, I'm not adding it as the last possible. I'm adding my new vertex as being something encountered on the path. Take a look at this thing. I now say you're now free to drive through Vancouver. I don't care how you get to Vancouver, and I don't care how you get to Vancouver to where you're going. We want to minimize. Okay, this is important to see. I'm going to yell at it again. It's important to see. You're allowed to use as many edges as you want in this one. Either you use it or you don't. Okay? Think about what the recurrence is. Once you think about the recurrence, you can see that it's true. It's a little tricky. If you don't see it, come back and ask. Okay? Meanwhile, good luck. See you at the exam on Thursday. Thanks a lot.